Okay, thanks for clicking on the video. If you weren't in class or haven't watched the video from last time, from 13.5, you really ought to do that because it gives a lot of foundation to what we're doing today. So as a warm-up, which will lead us into today's topic, we're going to take a look at a two-way table from last time. So this one had probabilities. So let's read the first question. What is the probability a randomly selected person attended the seminar and had an increase in sales? So when we're looking at strictly and, we're going to be looking at the intersection between seminar and increased sales, which is this number. And we always divide it by the entire total unless we're given more info. But we were just asked about an and, so we just give the intersection divided by the whole. So the answer to this was 0.48. What is the probability a randomly selected person attended the seminar? Okay, kind of an innocent question. No and. It's just asking what's the chance that someone went to the seminar. So at this point, it's just about looking in the table for the right number, right? This number here is giving the total for the attendance of the seminar, the probability. So that's the answer. And yes, we divide by 1, but that doesn't really do much. Again, these already have the probabilities in there, so it's a different kind of table. Okay, and then here's the kicker. What is the probability a randomly selected person had an increase in sales given they attended the seminar? So different than the last two questions because it has given. So the way we would write that is the probability of increased sales given that they attended the seminar. So last time we learned that if we have info, we can zero in on it. If we know they attended the seminar, because that was given, just like how we've had stuff given in proofs, we can take advantage of that. So I know that my numbers have to come from these three, okay? So the probability that they had an increase in sales was the 0.48. And we're not out of 1 anymore. We're out of the total that we are informed about. So 0.8 is our new total because it's in the column we've zeroed in on because of the given info. This equals 0.6. Okay, so this is the key, is that what we just did can be rewritten as a new formula. So the probability that the sales increased given that they attended the seminar is the probability of increased sales and attended seminar divided by what? Divided by this, which, because, right, that's what we divided by, right? And that was the probability of attending a seminar. So this creates a formula for us. And rather than keep talking about a seminar and sales, let's generalize it. So the conditional probability formula, which we just used in number 3, has this form. So two events, A and B, the probability of B occurring given that A has occurred. Remember, this line means given. So it's red. The probability of B given A is the probability of them both happening divided by the probability that the given occurred. Because remember, the given, if you're given something, it always changes the denominator, right? Okay, so let's apply this just frankly to a new question. So you roll a 6-sided die. What is the probability you roll a 6? Given you rolled an even. Okay. Well, the new formula says that when you have a conditional probability like this, you take the and divided by the probability of what was given. And that's how we answered those table questions. It's really the same formula. So what's the probability that you roll a 6 and it's even? Well, and this is one roll, right? So we just got to consider the options. So 6 is the only number that is both even and 6, right? 4 and 2 do not work because they are not 6. So the answer here is 1/6. And the probability that you roll an even, we know is a half. So now we know we can flip and multiply. So at the end of the day, we get 1/3. Okay. So if you have the information that you rolled in, because normally this would be 1/6, right? But if you had the info that you rolled an even number, the chances it's a 6 have now increased, right? That's the key in this. And this is the same takeaway from the last one. If you know something, it makes it more likely, as long as it's still contained. It would, like, the probability of rolling a 5 given you got an even number would be terrible, right? It would be 0. But the fact that we got more info that clued us in has made the chances higher for it to happen because we eliminated the 1, the 3, and the 5. So kind of interesting how this is working. So this is your typical textbook question here. So the probability of a volunteer receiving the placebo, so the probability of placebo and having a health improvement is 20%. Okay. 1/3 of the volunteers received the placebo. So the probability of the placebo, which if you guys know, it's a fake, harmless medicine that's given to people in these studies to make them think that they took the medicine. So it's still like, you can still have a control group, So the probability that a volunteer received the placebo was 1/3. And the question is, what is the conditional probability? So I know it's going to have a given of a volunteer's health improving given they received the placebo. So the last part is the given. And we're looking for the probability that the health improved. So the conditional formula is probability of B given A is the probability of both divided by the probability of the given. So it's the probability of both of them happening. Oops, I didn't mean to put a given there. And placebo divided by the probability of getting that placebo. Okay? Which we already wrote down what those were. This one is 0.2 and this one is 1/3, which we can flip and multiply and get 60%. Okay? Cool. So it was 20% initially of doing placebo and health improvement. But if you got the placebo, you're kind of halfway there. Not exactly half, but having like if you're looking for two things and you got one of them and you're given you have one of them, that's going to increase your chances of having the improved health. Okay. So this stuff is a little tricky, but we're going to trust the formula as we reason through this too, because it's kind of like it's a formula thing a little bit. So here we go, a little lighter question. So we got another breakdown of cats and dogs. So the question at first is the probability that a dog owner also owns a cat. So let's read that again. Conditional probability means I'm going to have a given, but I'm honestly not sure which is which. Should it go cat dog or dog cat? Okay. So what's the conditional probability that a dog owner also owns a cat? So this is a kind of a hidden way of saying that that's given, right? The people we're looking at all have dogs. So that is a given. What we don't know and what we're interested in is the probability that they have a cat. Okay, so it's the probability of cat and dog divided by the probability of our given, because that's the only people we're looking at. That should be our denominator. So 45% down here and 12% up here, which leads us to around this percent. You could also just leave. Well, no, I don't want you to leave it like this because having decimals in a fraction is kind of silly. So you need to write that. You either write that as another type of fraction that has no decimals, or as a percent, or as a decimal. So this would be okay too. Whoops. This would be okay. Something like that. I'll be more careful and tell you what to round to as well, if that's necessary. Next question. Flip, right? Conditional probability that a cat owner. So given that we have a cat, looking at those folks, what's the probability that they own a dog? So if we had a table, we'd be zeroing in on the cat column, right? So the probability of dog and cat, and I'm following the formula at the top, which is saying it's the probability of and over the probability of just the given. Okay, so the given in this case is cat. So the only thing the formula is going to change now is the denominator, because we're looking at different people. We're looking at the cat owners now. Okay, and this I got as around 44.4%. Okay, so yeah, that's that. So it actually does, the order matters. Okay, the reason why the cat, or why the second one is higher, is because owning a cat is actually more rare in this setup, it looks like. So if you know you have the cat locked down, it's easier to get the dog. Does that kind of make sense? That's why the percentage is higher. The probability is higher that you got the dog as well. Okay, so the second part of this are the tree diagrams. So you've made it through the first part. The formula that we talked about, you can play with it a little bit, multiply both sides by the probability of A, and get this, which turns out to be a really useful formula. Because this is really simple. We've seen a formula like this before. Remember in 13.4, we saw a formula that looked like this, that we multiply when we have and. But this was only for independent events. We have a formula that works for events that aren't independent as well. Okay, so this is kind of like the general case. Okay, so don't worry too much about the formula. Let's try and reason through a tree diagram, and I'll show you where we use the formula. Okay, and it's pretty intuitive, so I hope the video helps here. A college reported the following info about graduation. 70% of the freshmen so imagine all the freshmen are standing here. 70% of them decided to go public, which means if you only have two paths, public or other, this was 0.3. Okay, so we had some people decide, okay, I'm going to go this way, and I want to be a public student. Others decided I want to go down here, and I want to be an other student. I want to go to like a private school or something, or go into the workforce. 60% of freshmen who attended public schools, so we're looking at these folks up here, 60% of them decided that they graduate, or they were going to graduate within 5 years. So that would be 60% there, and it's kind of implied then that 40% did not. So only some of them, maybe only this guy made it up here, but the other guy trickled down and did not graduate, sadly. The people who fell into the other category graduated at a rate of 80%. So it's likely that this little man who went to other, it's likely for him that he actually finished out here and graduated. Okay? So the question is, what is the probability, or what percent of those freshmen at the very beginning graduated? So for our sake, when we had 3 people in our little picture, 2 out of 3 of them graduated. Okay? So we anticipate our answer to be maybe somewhere around 2/3. I don't know. I mean, not exactly, but we kind of followed the percents as we went a little bit. So the way this is going to work is we're going to track every path to graduation, and we're going to add those together. So we're going to take this path first. So let's write it out. The probability of going down that path, which is the public path and the graduate path. Our new formula here that I underlined and boxed in here says that it's the probability that you go public times the probability that you graduate given that you went public. But all that complicatedness, that yellow path, all it is a 70% chance multiplied to a 60% chance. So if you're a person standing here at the very beginning, there's a 42% chance that you're going to go down that yellow path. Okay? And the other path, let's actually leave that on there. So we're going to have a green path to success now. Again, we're on the hunt. Any way that we can find someone to graduate, right? And the other path, there's only 2, would be here, right? So the probability that you went down the other route and you graduated was the probability that you went down that other times the probability you graduated given you went down that other. But each of these over here or over here, they're just kind of stepping stones, right? You have to go down the other route, which was 0.3 right here, and then you had to go to the 0.8. Again, multiplying 2 probabilities together makes an and. And that's what we're doing here. The notation is just a little different, but this means that green route has a chance of 0.24. So those 2 paths are the only ways to graduate. So the probability that you graduate is 0.42 plus 0.24, which is 66%, which is pretty close to the 2/3 estimate we had earlier. Okay? So let's do another one. So this one does not have the tree, so we're going to have to draw it. So suppose a basketball team has a 75% chance of winning a tournament if their star player is able to play. This looks like a big given, right? So that might be the first thing that happens, is if the star player plays or not. So it looks like if the player doesn't play, they only have a 40% chance to win. But here's the kicker. The doctor says there's a 60% chance the player can play. The star player can play. So the beginning of our tree is going to be, you either got a 60% chance that you that the star player plays, or you have a 40% chance that the star player sits or does not play. Okay? So we got to branch these into two, and then that would be completing the tree. So we got to read the other sentences. So 75%, what is that talking about? It looks like it's looking at when the star player is able to play. So it looks like we're hanging out up here. So 75% chance versus the complement, the 25% chance. Looks like we're going to win if we're here. And it looks like if the star player plays and we don't win, then we probably lose. Okay. Now, if the player sits, we're in this sentence. Otherwise, the team has only a 40% chance of winning. So 40% chance to win, 60% chance to lose. So that player has a big impact. So what's the probability that the team will win? It's any way you can get to win. And we're going to multiply probabilities. So I want to keep this very straight and simple with you, and I'm not going to write out the whole formula. I'm just going to show you how to do it. Because I already wrote out the formulas for the last one. So I get to cheat a little bit. So to get to win, we can either go down this route, or you can switch it up and go down this orange route to win. Okay? The orange route is 0.4 times 0.4. And this was the green one. So you don't have to write out the complicated formulas. You really don't. But it's important to know that all these probabilities have names, right? This one is the probability you win given the star player plays. Right? This one is the probability the star player plays. Right? And it turns out that this formula links them together. But in the end of the day, it's still just multiplying. We just got to multiply all the possible paths that we can get there from. So this multiplies to 0.45. So these two together makes it so the probability that we win, there's only two paths to victory here on my tree. So I just add together those probabilities and make 61. Okay? It's important to note too that the other two paths, these yellow ones, if we found out what those were, they would all add, so the probability of a loss is exactly 39%. Right? It adds to 1. You either win or you lose. There's no other option with this setup. Okay? So the probability should add to 1. Okay? But this is our answer here. Okay? So, that's it. So there's a lot of homework for this one, but it'll pay off, and hopefully the test will be manageable after doing that. We're going to do some review as well before spring break, and we'll take the test before spring break, and then you guys are free to have your break.